Okay. Good morning, everyone. I have the pleasure to chair the first keynote speaker today. It's actually an honor to be the first one to talk. This morning we have the pleasure of following the presentation of Professor Pelton. Professor Pelton received a Bachelor and Master in Metallurgical Engineering in South Dakota School of Mine Technology, United States, and PhD in Material Science and Engineering at the University of California. He spent, some time as postdoctoral student in Stanford and Iowa State University and University of Notre Dame. Then he joined a research program on shape memory alloys, where he worked on processing fatigue, corrosion, and Nitinol medical devices, which is topic of this talk. Then he served as adjunct professor in material science engineering at Stanford, UC Berkeley, and Cal Poly State University, San Luis Obispo in California. In 2014, he accepted a position as Chief Technical Officer at G. Rao Incorporated, where he provides consulting and testing services to medical device industry. And also he co-founded the Shape Memory and Superelastic Technologies SMST organization, and he is associate editor of Journal of Shape Memory and Superelasticity. He was author of over 135 papers and edited 5 conference proceedings. And currently he holds 5 patents, primarily in the area of Nitinol biomedical devices. So just welcome Professor Pelton and enjoy his talk now. Thank you.
Thank you very much. And I'd like to extend my all right. So yes, I am honored to be here, and I thank very much Sabrina for constantly sending me emails to remind me that I'm 1 week, 2 weeks, 3 weeks, 1 month overdue. She did happen to contact me when I had COVID, so that was the first excuse. But then afterwards, it was me. So anyway, so thank you very much. It's a real pleasure to be here to share some work that I've been involved with for quite a few years. And in general, when we talk about cracks and medical device, we don't like to have those two come together. Okay? So therefore, we have to do a lot of research to try to understand their presence and more importantly, how to get rid of them. So we're going to talk about medical devices, okay? And these from stents to vascular grafts, the neurovascular devices to aortic heart valves, okay? And I'd like to acknowledge my colleagues, Max Lowney, Jochen Omer, and Willa Page. We'll see some of their work later on. Okay, so here's the topic list. First of all, what is nitinol? What are the applications? Look at the microstructural characterization, because as we will find out, that if the cracks that grow in nitinol are entirely linked to the microstructure. We'll see that. So we'll look at the way that we've characterized cracks in nitinol, both from fatigue perspective, from a total life versus the damage tolerant fatigue. We'll look at the crack paths in nitinol and some of the techniques that we've used to be able to monitor cracks. Finally, summary and next steps. Okay. So what is nitinol? What are the applications? Okay. So it's a nanometallic compound. It's nominally 50-50 nickel titanium. If you are not familiar with it, it's referred to as shape memory alloy, and what we observe is due to a solid state phase transformation. We'll see a little bit about that in a minute. So there's two different types. It's kind of a broad spectrum of observations. One is called shape memory, and one is called superelasticity or pseudoelasticity. And this little cartoon kind of says that if you have a rod or a wire and you bend it, you recover that, you put a strain into it, and recover that strain with heat. Or you can do like I have right here. I have a nitinol tube. I can take this tube and I can bend it pretty severely, and it fully recovers back to its original shape. We call that superelasticity. Okay. What we're talking about today is the superelastic aspect of nickel titanium for medical devices. So as I said, it's a solid state phase transformation. And what we're doing is we're going from a cubic phase, this is a V2 crystal structure, to a monoclinic phase right here. Here are the fraction patterns from those two phases there, and then the atomic structure that we have, okay? So you can well imagine with such a disparate change in the microstructures here, that cracks may go a certain direction in this phase and maybe a different direction or behave differently in the low temperature martensite. So this is austenite, this is martensite, and we almost seamlessly go back and forth with either an application of change in temperature or change in stress. Okay. So what are we going to talk about? Medical devices. And this is just kind of a montage of a bunch of stents out there. So maybe you know somebody who's had a stent. Nitinol is not generally used for coronary stents for your heart, but it's used all the rest of the body. Why? Because if you have a stent in your leg, you can still do this, and it's going to flex and go back to its original shape, we call it. Okay. So let's talk about kind of the types of strain that we have in the material, okay? So here's a stent, and it's being pulled into its delivery catheter, okay? So let's assume that it's a 9mm diameter stent. It's a self-expanding stent. So you pull it in, and you're going to put a high stress on it, high strain, and the values of the strains could be somewhere between 6 and 12%. The stresses could be up to 1,000 or 1,500 megapascal. So it's a one-shot deal for most applications. And once you have it in the delivery catheter, then the physician puts it into your leg or wherever it's going to be deployed, and it follows a completely different path on the way back. So it's a path-dependent transformation. So it comes down here in what we call the unloading plateau here, and there it resides into, for example, an artery. Let's say it's your leg, your superficial femoral artery here in the leg. Okay. So a 9mm stent inside of a 6mm vessel, and what we're doing is we're monitoring the strains of these little hinge points, if you will. And then once the cardiac cycle begins, you have the systolic and diastolic pressures of your heart that are pulsing through that now open vessel, and it's going to cycle like this. Okay. So there's a range of strains. The magnitudes go from maybe 12% here, and here is a strain amplitude of maybe anywhere from a 10% to maybe 2%, again, depending upon the application. Okay. So microstructural characterization. So over the years, we've done a whole lot. I'm a metallurgist. Metallurgists do microscopy, so that's what I do. So one of the things we do synchrotron X-ray microdiffraction, take a look at the structure and try to understand. And what we have here is a schematic of a dog bone, a simple dog bone. Okay, that dog bone was created from a piece of tubing, not unlike this piece of tubing right here that I have in my hand. And then it's rolled out and then laser cut into some kind of a dog bone. And it could go along the tube direction. We call that the zero direction at 45 degrees C, 45 degrees, or at 90 degrees circumferential. Okay. And what we do is we take a look at the structure here. And the reason I bring this up is because later on, when we start talking about cracks, you're going to find out, oh my goodness gracious, they take different pathways depending upon the texture, depending upon the direction of the applied stress restraint, for example. Okay, so here's right here. We don't have to go into details. This is an inverse Hall figure that tells us the orientation of the grains within, whether it's in the along the two axes or at 45 degrees. The different colors there indicate completely different orientations of the grains that we're looking at. Okay? Why is that important? So first thing we can do is we can do some in situ studies there at the beam line at the Advanced Light Source in Berkeley, and we can actually pull on these little dog bones and record the diffraction patterns along the way. Here we have 8 different views, if you will. So this is starting at 0, 0, all the way up here to number 8 for both ones. This is along the tube axis, the blue one here, and the red curve there is at 45 degrees. You can see this completely different set of mechanical properties. So when we're doing modeling, we have to ask ourselves, well, what direction is the stress or strain coming in? And then we have to use the appropriate stress strain curve. Okay? And what we see here, the black point here, that's the Martin site. So it stress induces the Martin site. All right. So the blue here, this is strain. There's different colors here. This is along the 0 direction. This is the 45. And you can see the pathways of the transformation are quite different depending on which direction we're applying the stress. So if you can imagine that the transformation pathway is different, then the crack pathway is also going to be different. And we'll see that coming up. We also do high resolution transmission electron microscopy. This is some work that I presented in Portugal a couple months ago, work that was done in collaboration with Stanford University. And what you see here are very elongated grains. The average grain size is nominally 100 nanometers. Okay? Why is that important? Because the studies that we did here for the synchrotron, we had to change the heat treatment to be able to get good signals. And so these grain sizes are 10 to 50 microns. But in reality, the material that we use for our heart valve frames is like 100 nanometers. Okay? Is that going to cause a difference? Perhaps so. Okay? So let's talk about total life versus damage tolerance. Okay? Here's a snap. This is a fluoroscopic image of a patient. This was a follow-up study of a stent that I worked on many years ago, and it's actually in the leg, okay, in the superficial femoral artery. Okay? I don't know if you can see right there, it's almost completely severed. It's almost completely severed there too. This is not an isolated incident. It is not an isolated incident. Why does this happen? I mean, for goodness gracious, we have a bunch of bright people working in the field. Why do we have fractures? This is the benchtop simulation of what we have right here. Why does this happen? So that's why we're studying this, obviously. So here's just the fracture surface, and I've just kind of outlined here the extent of the fatigue. We have an initiation point that we'll talk about what that might have been beforehand. So this is the issue. We need to understand about cracks and nitinol, because guess what? If this was in a heart valve frame and there's a fracture there, the patient's dead. We don't want that. Okay? For many different structures, if you see a crack, you say, okay, I've got another 10 years, I've got another 50 years before I have to worry about it. Patient's dead. Okay? So we do a lot of studies. This is some scanning electron microscopy of some nitinol wires, very similar to the composition that I have here in this tube. And what we did is just simple rotary bend fatigue, R-1 type testing. And we did this at a very high strain amplitude. This is a 10% strain amplitude. And what I wanted to understand is, yeah, we spend most of our time looking at the actual fracture surface, straight down on it. That's not as interesting to me. What's interesting to me is what does it look like to start? So this region here, this is the lower magnification. You see lots and lots of little micro cracks. Okay? You see that they have sometimes very tortuous path here. Okay? Here's a higher magnification of the same specimen, but way far away from the actual fractured surface. And what we see here, see these little dark gray areas here? Okay, this is in fact scattered state electron microscopy. So that gives me atomic number contrast. And what that tells me is those are inclusions. Okay? When we melt the nickel titanium, we form oxides and in some cases carbides. Oxides and carbides, as you well know, are ceramics. They don't bend. They don't have superelastic or sheet memory properties. What they do is they act as crack initiators. And what you can see here is that sometimes the cracks go from inclusion to inclusion and inclusion, and that helps define the actual path of the crack. You'll see some more of that later. Okay. And here's a study that my colleagues from the Food and Drug Administration, the FDA in the US, in collaboration with two big companies, Medtronic and Boston Scientific, they're doing fatigue tests up to 1 billion cycles. Okay? For a heart valve frame, 15 years for your normal cardiac cycle is about 600 million cycles. So they're taking it beyond that, that's beyond 15 years that the FDA requires, they're going to 1 billion cycles. Okay? And what they see is that every single fracture initiates at an inclusion. Okay? And you can see how ugly that inclusion looks like on the surface there. Okay? So let's move on to damage tolerant. Okay? Some of you may know my dear friend, Professor Rob Ritchie. Rob and I have done a lot of collaboration over the years, and Rob has stood in front of many international congresses and said, why in the world would anybody in their right mind use nitinol inside of a human body? Look at the fatigue properties here. Okay. So we have to calm him down. If Rob, please, you know, this is my livelihood. Okay. Here's a typical, we have crack growth rate on the y-axis, stress intensity range on the x-axis. This study was done with the first student in the field, Andrea McKelvey, who's now works for Apple and making, I don't know, 20 billion a year or whatever she's doing as a manager. Take a look at these data here that she generated. Okay. And you see that the threshold is very low. It's about 2 MPa per liter. And the rest of these curves here are from Rob's earlier work, from maybe 10 years before. So pure titanium, Haynes 25, nickel-based alloy, 316 steel, and 564. So all of them have much greater threshold values than nickel titanium does. Hence, this comment in Congress. Okay? So we'll talk a little bit about that. This was done, by the way, at an R value of 0.1. Just bring that up. So here's an interesting SEM image that was taken from the next student that came along in Rob's group, and that was Scott Robertson. Scott's done a lot of good work over the years. And what you see here is a crack pathway that is very tortuous, right? And this tortuous pathway creates the frictional interference that's starting to kind of arrest that crack. So we know that. I mean, those are the things that we look for. Do we have a presence or absence of this kind of pathway? Okay. But the reality is that if you do a typical ASTM standard CT type test and do damage tolerant analysis, you're going to find out that you need about 10 specimens put together to make up a coupon that you're going to be able to test. Because the medical devices are that much smaller than what's called out in the standards. Okay? So we're not really interested in large cracks. forensics, for example, for orthopedic, for spines or something like that, where the diameter maybe 5 to 10 millimeters or something like that, then maybe we can do that. But what we're really interested in here is the small cracks, okay? And how do those small cracks, A, start, and B, how do they propagate through the material? Okay. So we put together this table here. This is some work also from Rob Ritchie and Scott Robertson over years. And then more recently, this was just published this year with Louis Molino and Scott and Rob. And what they're looking at is kind of this, using the extrapolation that has been discussed with Suresh and Ritchie back in the materials review paper, that was in 1984, where you just do a kind of a linear extrapolation along from the pellet slope there. Okay, and you come up with a very small value of your threshold, and you can see that here. If the large crack has a threshold of about 2.5, then small crack is about 1/3, etc. And what Louis did, he did another experiment where he was focused on a beam on small wire and did the cycling, and what he was able to do is come up with a value of about a third MPa meter. Okay, very, very small. But those are the cracks that we're really interested in now. Okay. So one of the nice things that came out of Louis' paper, Louis, Scott, and Rob, is basically the next generation of a Kitagawa-Takahashi diagram. So Scott and Rob published one a few years back. It was very complicated, it had all different colors and stuff in there, and their color combinations that were ugly. This, by the way, is almost as ugly, but I didn't choose that. But here's the nice thing about this. If you're familiar with the Kitagawa-Takahashi diagrams, what you're doing is you're combining total life and damage tolerant events. And what you're looking for is kind of that intersection, which is right here. And so the delta K threshold for small cracks is this is the 0.34 MPa root meter right there. And it comes down here, you're talking about defect sizes on the order of 10 microns. Okay, we're going to come back to that. So from the earlier work of Robin and Scott, they said that the critical crack size was between 15 and 50 microns. Okay, this is a little bit smaller. Okay, so let's now take a look at cracks in microns. So again, going back to the work from Scott and Rob, and they let me get the work and then run it up. What we did is we do the synchrotron diffraction, and here are the two. We shape set up stores flat. We cut out C2 specimens and dog bones, etc. Then here we're doing it for monitoring the three-dimensional strain fields in the material at the crack tip. Okay, this is kind of a far field effect right here for this one, and we're right here. This first image is just the actual on YY. The loading path is close to 7.5 MPa root meters. Then go up to 15. Here, and you see immediately it's exactly what we'd expect. The strain fields around that crack are increasing. Okay. Again, the black area here, that's the marker site that's transformed. Okay. Then when you reverse it and go back down to the minimum, you notice the strain field escaped some of it. So we have residual stresses in the material that are probably remnant martensite. Okay. So we're looking at this and say, okay, this is great. We can give some information here. There's some good stuff that was written in the paper on that. Okay, but let's focus in a little bit here. Now what we're doing is we're the same specimen, same set of experiments. Here we're looking at the equivalent strain in this column here as a function of number of cycles. This is low cycle fatigue. We're not to 100 cycles here. And over here, we're monitoring the texture. So the beautiful thing about using synchrotron X-ray diffraction, first of all, it's free. The government pays for it, so I don't have to use any research funds for that. It's hard to get in there, and then you're basically living there for a week with no sleep, no food, but we get good data. Okay, so here's the thing. This again, we're looking at the martensite here, but there's a whole bunch of areas here that did not transform. Some of those grades were resistant to the transformation, and those are the ones that are near the 100 zone axis there. Okay, so I'm going to speed up here. So let's take a look at effective grain size. Now, finally, we have some work that Rob was not involved with. So this is really fun stuff that my colleague Will Page did. Actually, as part of this PhD program a few years ago. And what he did is he looked at different grain sizes of nitinol. This is rolled sheet. Okay, as rolled 10 nanometer grain size all the way up to 1500 nanometers. And you see the differences here. This is using the digital image correlation, the DIC, to be able to monitor the crack through the material. Okay, so one would say that if you look at the final result here, this is mode 1 crack. Okay, it's going perpendicular here to the stress axis, but this one here is not. It's a combination of mode 1 and mode 2 crack formation. Okay, very interesting. We won't go into a whole lot of detail. And then Will did some really nice stuff with higher resolution, where he actually put those specimens into the SEM, covered them with gold nanoparticles, and was able to do the DIC inside the SEM while he was straining it. So he did one big cycle inside the SEM and watched the crack and look at the strain fields at the tip of the crack. Okay, there's a lot going on here, but what's interesting is that the SEM here, that the micro cracks, there was a lot of, we observed a lot of crack bridging, which we would expect to see. The 1500 nanometer, the largest grain size, had the largest, the smallest crack tip opening displacements, and the rougher surface on the fracture later on. And I'm just about done. And then we'll also get some work looking at the different orientation. Okay, we won't go into the details of that, but let me just come to the summary again. Okay, so we do observe cracks in nitinol, and we hope that that'll result in deaths, right, in the patients. That's the thing that keeps me up at night. Okay? The cracks that we see depend upon the product form, and a lot of the studies were done with sheet because it's convenient. We don't make products out of sheet. We make it out of tubing. We make it out of wire. In general, depends on the orientation. Sometimes it's more convenient if we go this way, but in fact, from a fracture perspective, we should be going in the opposite direction, or 90 degrees from that. It depends on the grain size. Can we monitor that? Can we optimize that? And the other thing is, you saw a lot of the earlier images with cracks right at the inclusions, the oxides and carbides. What if we were able to, we can't eliminate them, what if we minimize their size? What if we minimize the volume fraction? Would that then change the crack path through the material? Okay? And that's basically what I'm saying here on the final slide right here. So with that, hopefully I'm not too late. Okay? And thank you very much.
Okay, thank you, Professor. We have a lot of time for questions.
Thank you for the presentation, very interesting. A couple of, quick questions here. Being delta K or K, the stress intensity, being developed in terms of isotropic, continuum theory, don't you think it's quite surprising that it will work for sort of quite anisotropic material? And further, we are taking it to the very short crack size where perhaps small scale yielding conditions do not hold all these sort of things. And the last comment, wouldn't it be better, as you mentioned, you don't want cracks in this thing, to see cracks there. It doesn't matter the size, it can be quite dangerous. So wouldn't it be better to use sort of safe life design, doing a modeling in terms of stresses rather than in terms of K?
So you do know I have jet lag, and you gave me like, was it 6 or 10 questions? Let's see if I can remember. Okay, look, delta K just, for all the reasons you mentioned, they don't really work with nitinol. Nitinol it's too different from your normal linear elastic material. You know why we use it? Because there isn't anything out there. Okay? That's number one. Number two, what we're actually doing when we're doing these tests, whether on the benchtop or in theory, because we have some other models and stuff, is they're all proportional to the load, right? To the P. So we can say, okay, so it's not exactly correct, but it's giving us something that is getting us in the direction of the answer. It is not the answer. And I have a lot of friends who are spending a lot of time on computers trying to come up with models. They don't like K, they're using J, and they're doing a whole bunch of other modifications to it so that maybe we can really get at something that would be more predictive than basically what we're doing is just reporting with this. Okay? And we're saying, hey, you know, if you compare a 316 standing still to nitinol, it's much different. Why is that? Because one is in stress control and one is in strain control. Okay, and the moduli are much different. So we do use safe life design, and I spend a lot of time interacting with the FDA. And the FDA told me many, many years ago, he said, Alan, there are 3 things that I want you to figure out: fatigue, fatigue, fatigue. Okay? And that's what I devoted my career to do, is looking at fatigue as I know. So, but thank you for your insights. You're absolutely right. It's the best model we have now. We want to do something better.
Any other question?
We have time.
Yes, yes.
Thank you. David Taylor from Dublin.
All the way from
Nice to
Dublin,
see
from
you.
Trinity College, my good friend.
Well, all the way. I thought you'd be remote, so here you are. That's wonderful.
Give him a chance to come to Italy.
And a great privilege for us to listen to the expert on nitinol. So thank you. So this story of the inclusions, which of course has been going on for quite a while now. A silly question is, why don't we just get rid of them? And slightly less silly would be, can you speculate, if you could get rid of them, how much better would nitinol be?
Great question, as always. So the question about inclusions. So let me take you back when I was a young lad, real young lad, 150 years ago, when I started in the still. And we had oxygen contents in our nitinol that were something like 1,000 parts per million. Okay? We're now down to less than 400. We have improved. Okay? We now have material that have inclusion sizes that are like 2 microns. Instead of the ASTM standard, ASTM F2063 allows us to have 39 micron inclusion size. And if you remember the Takahashi diagram, that's over in the area where we have to be concerned about those defect sizes. When you're in about the less than 10 micron range, now we're actually getting, from a total life perspective, we're having increases in 200% in our fatigue life. Okay? So there have been improvements, but you know what? What we're doing is we're basically doing testing so we can pass things on the FDA. That's my business, right? I work with clients, so I can help you get to the FDA. On the side, what we're trying to do is now the next step is to employ some of these techniques and say, What if I have a dirty material, like the stuff that I have on my ankle, and some of the newer material, and see if we see some differences in the crack paths and some of the other properties? But that's a great question.
What to do? Thank you.
You're welcome.
Comment?
Thank you for a great talk. Maybe a silly question. What are the inclusions made of? Or is there only one type of inclusions, or can it be anything? What is it?
There are two primary types of inclusion in the material. Okay, those materials, those nitinol ingots that are melted with vacuum arc remelting, which is more than half of them out there in the market right now. Those have they have oxides, only oxides, and it's a Ti4 Ni2 oxide, and it's modeled after an intermetallic compound of Ti2 and I. Okay, so that is the primary. The images that I showed you from my rotary dent fatigue work, those are all oxides. On the other hand, there's another melting method that is vacuum induction melting, and they use a graphite crucible, and that contaminates the material with carbon, which forms TiC. Okay? And in my opinion, those will work because they have nice sharp edges because they're cuboidal, they're cubes. Okay? So those are the two primary inclusions that we see in the material, and we really are trying to get rid of them.
Short comment, please.
Thank you.
Yeah, I was just wondering, what is the size of the specimens that you use to generate the data? And what is the size of your actual? Do you have to include anything called a size scale effect or fracturing approach?
Yeah, good question. So, for example, the ADN type pressure mechanics type test that we did, whether they be sheet, there was about 1 millimeter in thickness. So actually, under those conditions, we're in plane stress. And when we unwrapped the tubing and made specimens, CT specimens in there, that was maybe like 400 microns. So again, that was in plane stress. So those are comparable to like the wall thicknesses of our stents and heart valve frames. And yes, there is a size effect. So some of the early work that I talked about, Andrea McCulvey with Rob Ritchie, she worked on CT specimens that came from bars that were this big in diameter, that sliced from it, and EDM cuts everything. Their data is not too different from the data that Scott Robertson generated from the tube specimens, but there are differences. So there are size effects that come up, and probably orientation effects, et cetera, that we have not yet accounted for. Thanks for the question.
Okay, great. I think time's up. I'm receiving some messages from the chairman. So we thank Professor Pelton once again, please.